Um, so yeah, thank you for having me. I'm so sorry for being late. I have no good excuse. I just lost track of time. I'm Aaron Halfaker. I'm just showing you a picture of the Wikipedia page about me, which I had nothing to do with. I just want you to know. Sometimes I post on the talk page of this to ask questions or say like, "Oh, I was in the news," just in case you want to cite something new. But I just wanted to call this out because it turns out some of my past work working for the Wikimedia Foundation is also displayed on my page. This is because I have something special installed inside of Wikipedia so I can see these predictions, but these are an article quality prediction, which means that it's C quality, kind of a middle quality, and some topic routing predictions. So you know that it's about a person because it gets tagged with biography. Apparently I'm into internet culture, but computing and technology seems like a pretty good assignment for me. Um, so I worked for Wikimedia as essentially, building machine learning models for about 10 years before I started working at Microsoft. I now work at Microsoft doing a lot of things with large language models. I'll be talking to you a little bit about that today. Um, as was said, I'm going to break this talk into 3 parts. First, we're going to talk about large language models because I think that's what people will be less familiar with, at least the things that I want to talk to you about them. We'll get into a little bit of what's going on in Wikipedia, and we'll try and bring it together with LLMs, Wikipedia, and science literacy. Okay, so first, what is a language model? Well, a language model is really just something that predicts the next word. And so we start with, in this example, I have a lovely, and the word bunch is very likely to come after that. Whereas 2016, probably not very likely, little, not very likely. And so the language model will say, okay, well, I'm probably going to select bunch to come after I have a lovely. So we stick bunch in there and then we ask, well, what comes next? And that's now it's very, very likely that we're going to put coconuts in there. And so if you're familiar with the song, I have a lovely bunch of coconuts, you can see that the language model sort of knows the song and can complete the song if you start saying it. This was sort of, oh yeah, so I just want to give the example here. If I just give it the prompt, I have a lovely, it'll complete. This is, by the way, OpenAI's new Scallion GPT model is doing this completion. You'll see any completion that I have here is probably the Scallion model. So I have a lovely bunch of coconuts. There they are standing in a row, big ones, small ones, etc. You can see also how it can complete a statement about Seattle. So Seattle is the largest city in the state of Washington, the Pacific Northwest, etc. So you can see how this essentially, this is a language model producing really interesting knowledge content by just predicting the next word. And that's literally what it's doing. After the city of Seattle, it predicts then it predicts largest, then it predicts city, etc. That's what's happening here. And this is what essentially the state of the art as of GPT-3, which is actually a really old version of GPT at this point. It was trained on the Common Crawl, which is essentially, you can think about it as the entire internet and all digitally available texts. But there was a major advancement that happened with GPT 3.5, where essentially they gave the model about 1 million examples of following instructions. So essentially you'd have like a set of instructions and then you'd have examples of those instructions being followed. And that essentially teach the model to not just complete a statement, but to essentially be able to ask it to do something and then it will try to do that thing. And so here's sort of an example of the difference between these sort of instruction tuned models and not. We have a chunk of code here that's going to compute a binomial coefficient. We ask like the old version of the model, what does this do? And it doesn't quite know that we're asking it a question. It's just trying to complete some things. And so it says to store the value of some numbers inside of this C array. Whereas after we give it instructions, it understands, oh, we're asking it a question, we're giving it some code, so it should describe the code. And so it says, oh, this is a list, the list C in this code is used to store values for a binomial coefficient, etc. And so you can kind of see the dynamic shift in how you can interact with these models once we tune them on instructions. And so now we can ask it something like, what should someone do to get started as a Wikipedia editor? And rather than completing this by asking another question or something like that, it understands this is an instruction and it responds with a relatively well-structured response of, you should create an account, learn the basics, start editing, use the sandbox, etc. And I wanted to give an example here because, so I'm a computer scientist, and so, but I know that we're in a physics space here, and so I wanted to give a question that's a great example of an overlap between computer science and physics. So I asked, what's the relationship between computational complexity and physical systems? Could I design a physical process that could solve a non-polynomial problem in polynomial time? And if not, why not? And whoops. I lost my slide of the answer, but I just want you to know it was a really well written answer, something that I would expect for the quality of something that might be written on Wikipedia. Um, and so, what I really want to talk to you about is essentially we can think about GPT like systems, these large language models, as you give it a prompt and it gives you output. You're essentially giving it instructions. You might give it some information that it can work through in those instructions, and you can do powerful things. I was just showing you examples where we ask it questions. We can ask, who is Jamie Tivan, which, by the way, is a famous computer science researcher, works at Microsoft, and it will give you a response. But it turns out this response, it's mostly not right. It's actually out of date. She no longer works in Microsoft research. Actually, she might still be an adjunct professor. I checked in with her about this, and I think that she actually might be. So anyway, but at least some of this is out of date. And that's sort of a problem that we have with these models is you feed them information and they can reflect that information. But if they haven't been trained recently, they haven't been fed information recently, then they're out of date. And this is sort of how these models operate. They're usually about a year out of date whenever anybody's using them, sometimes more than a year out of date. They're also really bad at math. If you ask it the square root of 42, it'll tell you that it's 6, which anybody who can do basic math would say 6 times 6 is not 42. And so it's kind of, it's not terrible, but it's not great at doing math. So I want to talk to you about advanced prompting methods, how we can help these models be smarter and do more things. So one of these ways is chain of thought, where we actually tell the model to consider a step-by-step process by which it might address the user's question. We can show it examples of following a step-by-step process. This paper uses a lot of math problems, like word-based math problems for this. But I'll show you a real simple example with going back to the square root question. So if I show it, hey, you can approximate a square root by just taking squares that are around the right number and then working through some decimal places. Why don't you try that for me? And it does actually a pretty good job. It turns out that it's still bad at math. It still doesn't actually quite get the answer right, but it's much closer than it was before by having it go through this step-by-step process. You might be familiar with this if you've ever taught a math class to kids. If you have them think through their math, they do a better job. We're going to see lots of similarities between people and LLMs in this regard. People are also bad at math. Okay, so chaining is another thing that we can do, and this is where we can employ complex reasoning patterns. And so I want to give you the shape of this before I give you an example. Essentially, we run a prompt through GPT, we take its output, we put that at the end of our prompt, and then we run it again and run it again and run it again. And by this way, we can essentially allow the system to think iteratively as it goes through a problem, and we can feed information into the model in this way. So one of the most seminal papers here is this paper about the React system, where it's trying to get reasoning and acting to work together with language models. But the gist of this is this. You give it a prompt that essentially says, hey, you're an assistant, you're going to do some stuff. We're going to give you some tools. You can search the internet, you can use a calculator. And we want you to essentially follow the process where you have a thought, you decide which tool to use, you tell us how to run the tool, we tell you what actually happened when we ran the tool, and then you go again. And so we get into this nice append format, which we'll see in just a second. So let's ask it a question. This question I happened to ask was, how are Brent Hecht and Jamie Tivan related? Oh, sorry, actually, before the first example is, let's actually do the square root of 42. It says, oh, I'm going to use my calculator, which, by the way, is just write some Python code. I go execute the Python code. I give it the output of the Python code, and it says, oh, well, here's your answer. I know the answer to this question. So it's actually pretty good at using a calculator. Again, humans pretty good at using calculators, pretty bad at math. Okay, so we can solve this problem by essentially giving it tools, appending these things to the prompt and saying, okay, now you have the final answer. You can answer this question. So one of the really interesting things when we think about sort of like a Wikipedia context and information context is, well, how do people make sense of information? So there's a lot of work in this space. I'm drawing from some work that's from like the search engine literature. They call this pattern by which people use search engines to like make sense of a question that they have, information foraging. And they draw from a lot of the literature on how, say, a squirrel forages for nuts and that sort of thing. And essentially what we're looking at in this graphic is that the user starts out with a query. They're like, oh yeah, I want to know about X. They search what is X and they get some results back and they realize that there's actually something more that they want to dig into X. So they get some new terms that they can use in their search queries, and they formulate another search query with some new terms in it and learn a little bit more about that. Based on those results, they now know better what they want to search for, and so they run a couple more queries, use a few more new terms in the process, and get some new documents back. And after they iterate on this a few times, now they finally understand enough about what they're searching for to know what they're searching for, and they can get exactly what they need. Anybody who's sort of dug through old internet stuff to say, I don't know, find a ROM of an old game knows this pattern very well. And you certainly would know this if you went down a rabbit hole in Wikipedia. So we can have the model do this as well. And so essentially, we tell the system, like, hey, you're going to go dig for information. You're going to use these tools. These tools will let you gather information as you go. You're going to have thoughts. We're going to give you observations. You're going to have follow-up thoughts. Um, and so let's look at this question. How are Brent Hecht and Jamie T. Van related? These are two computer science researchers. And so the first thing it does is let's just run a search for those two names, Jamie T. Van, Brent Hecht. And it gets some results. We stick those results at the end of the prompt. We run the prompt again inside of GPT. It can now see that it ran a search, and it can look at those results and come up with some new terms. And it can say like, oh, well, I'm going to search a completely different tool. I'm going to search your email history. This is, by the way, like I do a lot of work with searching within an organization. This generally doesn't search your email history. Sorry, we can get into the details later if there are questions about that. But just think about this as it's just gathering more information. And then it can go again. And so this time it ran into something called the Office of Applied Research, which is an office I used to work in at Microsoft with both Brent and Jamie in it. And it realizes like, here's a new term. This is something I need to learn about. To learn about their relationship, I need to know about the Office of Applied Research. So it searches for that. We again get some results. We append them to the end. And it says, okay, I'm ready to respond to the user now. This is my final thought. Sorry, the results indicate that Jamie Tiva and Brent Hecht have a professional relationship. They work at Microsoft. I actually truncated this result. It talks a lot about their work in the Office of Applied Research. So you can see how it progressively works through information sources to get up-to-date information in order to answer a complex question. Here's the actual final result. And note that I've told this model how to put references in place. So we're starting to look at something that looks a little bit like a Wikipedia article here. We now have an answer to a complex question. It involved gathering a bunch of reference material and citing the material in its response. So one thing that I wanted to call out here is there are some more simplistic models that you might be familiar with. For example, if you ask ChatGPT with some tools to do this sort of thing, it will essentially take one round of running those tools. And so it might run 3 searches where it runs, the name with some professional background, the name with their relationship, and it roughly gets the exact same search results and gives us a really simple answer that they both work at Microsoft, and Jamie is doing some stuff with productivity. But what I just showed you in the previous slides was an iterative pattern where it runs searches, it has a chance to think and update it how it wants to search, then it runs some more searches, it updates how it thinks and runs some new searches. And so we first start out by searching Jamie T. Van Brent Hecht, but then the next search is Office of Applied Research at Microsoft, which the model wouldn't know anything about except for looking at the results of this first search. And so we call this sort of an iterative planning pattern. And it looks like what I would argue what Wikipedians do when they write articles, what anybody does when they're trying to make sense of information. We usually just don't run a pile of searches and say, okay, that was good enough, I'm done. At least not if we're not being lazy. The most important thing about this is that at each step of the process, we learn things. And so we can say, okay, well, based on what I learned, what should I do now? Now I learn new things based on what I learned. What should I do now? Anyway, this is a very powerful way to use these models to solve complex information problems, and I hope that at least a bit of that came through. I just want to call out that these kind of approaches are really important when an information need is unclear. When we're dealing with low relevance search, if you've ever searched, Gmail or Outlook, you know what I'm talking about. And especially when there's a high level of term and concept ambiguity, like at least inside of Microsoft, Garage Blast has a very particular meaning, and it has nothing to do with the garage exploding. If you search Garage Blast inside of Bing or Google or something like that, you're going to get news articles about people's garages exploding. It turns out Garage Blast is a newsletter, by the way, inside of Microsoft. Okay, so now I want to talk to you a little bit about Wikipedia. Actually, why don't I stop here for just a second? I kind of blew through this really fast to try and see if I could get through this material. Maybe I could take a couple questions before I move on. Wikipedia, but I can't talk about Wikipedia. Oh, let me say that again. I can't talk about Wikipedia without talking to you about planet Earth. So planet Earth is about 7.8 billion people. It's actually, I think, up to 8 billion now. I don't know. I have to keep updating this slide. Well, there's about 1.6 billion people who read Wikipedia about once a month. So about 1 in 10 people on Earth are reading Wikipedia once a month, which is a pretty big ratio. Um, but when you look at Wikipedia editors, there's about 110,000 of them that edit Wikipedia about once a month, and that's about 1 to 10,000. So one editor per 10,000 readers of Wikipedia. I just want you to know that, like, this pixel, that's way too big. I can't make it small enough on this screen. Let's zoom into this spot and talk about what's there. So we have 1 to 10,000 editors to readers. And then we have, like, the Wikimedia Foundation, the organization behind Wikipedia that supports the editors, keeps the site online, fights legal battles. They're a full-on corporation, have a HR department and all that sort of stuff. They're about 400 people. So they're about 1 to 1,000 with the Wikipedia editors. Um, and so that should give you a sense of scale about what we're dealing with Wikipedia, where the paid staff are, where the volunteers are, and how that reflects the entire population of the planet. So I want to talk about what Wikipedia is. You might be familiar. It's the largest encyclopedia in the history of humanity. It's got about 5 million articles in English Wikipedia. If you really want to see what's in Wikipedia, I really recommend going to this article called The List of Lists of Lists. And so this is exactly what you might expect it to be. It's a list of all the lists of lists on Wikipedia. And to show you what's in here, let's just pick the first one from the list. We'll go to lists of ancient kings. That brings us to another list of lists, which is the first one on this is the list of pharaohs. So we click on list of pharaohs. This is actually a list, but it starts out with a little bit of discussion. But if I pick the first item in that list, it turns out that that gets us to Ptah. And by the way, I know how to pronounce Ptah because we have this wonderful pronunciation guide at the start, and we know that the P is actually pronounced at the beginning. But this is a wonderful way to browse Wikipedia and see what's there. You know, the search box or just going from article to article is a great way to do it, but I highly recommend the list of lists of lists. It's sort of like sitting down at a traditional encyclopedia with like a shelf of books and just starting on a letter and seeing what's there. But I would argue a much better way to do it. So, but the interesting thing about Wikipedia is that it's a wiki. Anybody can edit this. We have shared authorship. This is arguably why it's gotten as big as it is. It flips the publication model where you publish first. Anybody can make any edit at any time, and review happens later. Maybe, but I should really make that maybe almost certainly. And we'll get into that in a little bit. It's an online community. Like I said, it has about 110,000 active volunteers. They have web forums, just like any other online community. And so they call them village pumps. There are some dedicated to policy discussions, technical discussions, proposals, ideas, and anything that doesn't fit into any other group. They also have subject matter focused working groups like Wiki Project Video Games that works on articles about video games, Wiki Project Medicine that works on articles about medicine. I'm sure there's Wiki Project Physics. I know that there's Wiki Project Chemistry because I worked with them quite a lot. Um, I just want to call out, like, the ridiculous amount of research that has happened on Wikipedia. This is a Google Scholar search for Wikipedia governance. And it says that there's about 37,000 articles. That's probably not quite accurate, but I just want you to know if I scroll to page 10, out of these results, there's still quite a lot of research papers about governance here. So there's at least 100 papers about how Wikipedia should be, or shouldn't be governed. Lots of other topics in this space. And so I'm going to summarize a little bit of that research for you. Okay, so the way that we make rules in Wikipedia is essentially there's sort of two different types of rules. One is prescriptive, a thing that we should do, versus descriptive, a thing that we've been doing and should probably write down so that we can keep doing it and people can understand it. So either way, either it's a proposal or a description of what we're already doing. We write an essay, then we have a discussion. We pull in a lot of people to discuss what's going on in Wikipedia. Should this become a rule? Should it be described in this way, etc.? And if that passes that discussion, then it becomes formalized as a policy or a guideline, which are essentially the formalized rules in Wikipedia. If it doesn't pass that request for comments, then it goes back to being an essay, and we can still cite it and talk about it, but it's not considered a formal rule. And so this divide between formal and informal rules is something that's sort of highly discussed in Wikipedia. And I want you to get a sense for what formal and informal rules look like. So an informal rule is don't stuff beans up your nose. Anybody who has kids knows that if you tell a kid not to put beans in their nose, the first thing they're going to do is put a bean in their nose. And so this informal rule is really about don't tell the vandals not to do something that they haven't done, because they're probably going to do it right away. So don't give them any ideas. Whereas a formalized rule on verifiability says that essentially all assertions of fact need to be supported by a reliable source. And so you can see there's a clear divide here between the seriousness of formalized rules and the not seriousness, yet still importance of informal rules in Wikipedia. These are highly cited as people get into discussions about what articles should be shaped like, what they should be, etc. Oh yeah, so this is the don't stuff beans up your nose. Of course, I had to show you that. Okay, so a big question about quality, like is Wikipedia trustworthy? Well, the internet, if you will, is constantly dumping content into Wikipedia. Um, there are about 160,000 edits to articles in Wikipedia that need to be reviewed for their quality per day. There's about 1 to 2,000 new articles that get created per day. Um, there's over 300,000 articles that are tagged as needing some cleanup and attention, and there's also about 1,600 newcomers that show up in Wikipedia per day. So it's just a massive amount of stuff that comes in from the internet. So essentially, the way that Wikipedia deals with quality is by having filters that hit things right after they show up in Wikipedia. So I'm going to put a divider in between the internet and Wikipedia, but you should imagine this divider being right inside Wikipedia, right after something gets published. It's going to hit some review. So we have people who do a lot of work in Wikipedia that's primarily curating content, reviewing stuff that comes in, making sure it's reasonable. I'm going to call them curators for a moment. And so it's their job to separate the vast majority of good stuff that's coming in from the relatively small amount of bad stuff. So the bad stuff doesn't stick around in Wikipedia and the good stuff sticks. So the way that this works is there's essentially different filters that happen along the way, and they happen at different time scales. Um, and so I want to talk to you sort of about the history of quality control in Wikipedia at each of these timescales. So first, when Wikipedia was young, they developed this page called Recent Changes, which essentially showed all of the recent edits that have been happening to everything in Wikipedia, all of the discussions, all of the changes to articles, all of the changes to policies and guidelines, etc. And it was the job of the curators to filter everything out at that one place. And it would usually happen about 1 to 10 minutes after a change happened in Wikipedia. They had to filter out everything from subtle problems and hoaxes and that sort of thing to obviously bad stuff like racial slurs, curse words, that sort of thing. And so that was the one filter that was in place. And that worked pretty well until Wikipedia got big. Um, and oh yeah, so yeah, there's our racial slurs and curse words. We have bad stuff, which is so and so is gay, which is sometimes true, but often is vandalism, dubious claims, unexplained removals. And yeah, for subtle problems, we get hoaxes, undue weight, which we can go into what some of these sort of subtle problems are later if people are interested. And we have these recent changes patrollers who are the main curators who are operating at this time scale. Okay, so to see how hard their job is, let's look at some subtle problems. Let's try and guess if there's hoaxes or not. And so usually I have people raise their hand for this. Maybe you can vote in the chat whether you think something is a hoax or not. So we're looking at the article for Ronnie Hazelhurst, and we're looking at an edit that added a pop song to Ronnie Hazelhurst, a pop song called Reach, I guess, or maybe S Club 7. I don't know. We're linking to a pop song here and we're adding it to this article for this person. I don't know anything about Ronnie Hazelhurst, so I can't tell you any more about this. Most of the time, recent changes patrollers, this is all that they're seeing. So put your vote in the chat. Is this a hoax or is this not a hoax? Is this a good contribution? Is this not a good contribution? I don't see any votes in the chat. Maybe people are thinking. Yeah, exactly. How on earth would we know? That's a great question. So I'm just going to skip ahead and say this is a hoax. And it turns out like this is really hard, and so like I just want to give you another example. So the monarch butterfly, you might know something about a monarch butterfly. This contribution said it was nominated as the national insect of the United States and the national insect of Canada. Um, and I'll just skip you the trouble here. This is also a hoax, but it looks reasonable, right? And we have another one that only registered users can create new articles in Wikipedia in the English edition, but in the other editions, they can create new articles without registering an account. And I'll tell you, this one is actually true. Only in English Wikipedia do you have to register an account to create a new article. All the other language editions of Wikipedia, even anonymous users, can create articles. Um, And so essentially, one of the big ways that they address this subtle problem pattern is watch lists. So if you're registered on Wikipedia and you look at the top of the article, you'll see this little star, which is empty before you click on it. If you click on it, then it will add this article to your watch list. And what that does is it gives you your own specialized recent changes feed for the articles that you care about, the articles that you know something about. Um, and what this allows people to do then is review things that they have expertise in. If you know about monarch butterflies, you're probably going to know if that contribution was a hoax. If you know something about Ronnie Hazelhurst, you might know if that contribution was a hoax. And so what this essentially does is it routes changes to topic interested individuals, people who would likely have expertise in this area, and it makes these kind of subtle judgment calls a lot easier. So some articles don't have people watching them. Some articles have a lot of people watching them. But this largely scales with importance and popularity. The most popular and important articles have lots of people watching them, and articles that are much more obscure have few to zero people watching them. And so what this does is it moves subtle problems out of the issue of the RC patrollers. So RC patrollers can say, I don't know about this, it looks good enough. And the people with their watch list can say, oh, actually, this is a hoax, or actually, I know for a fact that this is good enough. And so you can see how this is starting to become a staged filter process. Regretfully, watch list issues generally get caught on the scale of 24 hours because people tend to check their watch list when they log in, and a lot of people who edit Wikipedia regularly log in once a day. This is more like 12 to 24 hours. Okay, so this worked great until Wikipedia got huge and turned into an enormous fire hose of new content coming in, as I described earlier. We're looking at the number of active editors in Wikipedia over time, so you can see this growth period between 2004 and 2007, where Wikipedia became a fire hose. It's still a fire hose during this decline period. I just want you to know, spoiler, the decline flattened out. It's not declining to zero. We can get into that later if you want to. So of course the RC patrollers were said, turn it off. And there was a big change that happened around this time where we invested in machine learning models, technology that can essentially filter out the edits that might be bad from the edits that are almost certainly okay. And so essentially filtering this fire hose. And so without these machine predictions, it would take people about 167 labor hours per day. So about 33 people doing 8-hour days to review the 160,000 edits that we get to articles in Wikipedia. But with machine prediction, we can filter that down quite substantially and make it so that only 4 people doing about 8 hours a day can filter this 160,000 edits in Wikipedia. And that's sort of what happens right now. We have about 4 people actively patrolling Wikipedia at a given time. And so now the current state of Wikipedia is that we essentially have a filter that's mostly robots and people who are using robotic tools who can remove an obviously bad change at 5 seconds. Then humans using these tools can remove the stuff that's not obviously bad, but is still bad on the scale of 1 to 10 minutes. And then we have the watch listers who can remove subtle problems on the scale of 12 to 24 hours. And I just wanted to call out that artificial intelligence plays a really big role for the first 2 points in this filter. And we can actually see these things play out in practice. This is just a figure from one of my papers that shows like who's doing the reverting of bad content in Wikipedia and what time scale do they operate on. You can see how I was saying that it's more like 12 hours for the watch listers, but it kind of extends out to 24. I just wanted to call out that that's a much later time scale, but there's a lot of overlap that's happening here. Okay, so this is a big argument to like, is Wikipedia high quality? Should you trust it? It's like, wow, it actually has a really robust filter that works really well. It's fast, it's high capacity, and it's very effective at removing content from Wikipedia. It's actually so effective that it's causing problems, but that we can get into another time. Okay, final bit is pulling this all together, and I want to leave time for questions and discussion. So I just have a little bit here, so I'm just going to try and cover it really fast and make the connection between what did I talk to you about LLMs and what am I talking to you about Wikipedia and what does that have to do with scientific information. So a huge part about this is quality is a process. It's not an artifact of the thing itself. And so this is something that at least I was introduced to this concept from the citizen science literature that studies people who are going out in the field and taking measurements and aggregating them together so that we can know things about, say, water quality in lakes and that sort of stuff. This photo is of somebody taking a water quality measurement in a lake. And the paper that I have screenshotted here is all about how the quality isn't inherent in the measurement itself. It's an artifact of how the measurement was taken. And so when we have people record how they took the measurement, then we can filter out bad quality measurements versus good quality measurements. And I think we should think the same about Wikipedia. So I would say Wikipedia is a process, or at least a large collection of processes that are focused around quality. I talked about watch lists. I talked about these new review processes. There's also a lot of work around manual style development. We have robot editors that are doing more things than just reverting bad stuff. They're doing normalization and cleanup and that sort of stuff. There's a huge amount of processes that are in place. And further, Wikipedians themselves, when they're contributing to articles, are following this information foraging literacy process that I described earlier as they gather information, search for new information, figure out what's actually relevant, and contribute that to articles. Um, so essentially, I would argue this information foraging process is roughly identify a topical space, gather relevant reference material, search and discovery, just like an LLM does in my example earlier, make sense of this reference material, which is largely a literature review, summarize this into Wikipedia's format. It will then get caught by watch lists and people will come to review the stuff. And then you engage with those reviewers if they come back and say, hey, something's an issue here. And there's a whole bunch of process around how to do this stuff. I'm just going to wave my hand at that. This should sound familiar because this sounds a lot like a scientific process. In the same way, if you want to write a scientific research paper, you identify a topical space, you gather relevant reference material, you make sense of that reference material. You do something new that Wikipedians don't do, which is gather new data or produce new insights. You summarize it into the appropriate format, and you engage with reviewers. And so then I would like to pose that can AIs implement this process? That's exactly what I was showing you earlier, is that with a little bit of clever work and these language models, we can actually have these language models produce well-sourced and reasoned literature reviews of content for Wikipedia. So in summary, LLMs can reason over documents like humans. Wikipedia has a robust quality control systems, and the processes that Wikipedia and science use are similar. And also language models can do that too. So should we have language models write Wikipedia? Let's discuss.